Hello, we will be continuing our discussion on computer networks and internet protocols. We were discussing on physical layer phenomena. As I mentioned earlier, that physical layer is the lowest layer in the OSI or TCP/IP protocol suite. In some of the cases, physical layers are kept apart from the actual network protocol suite because of the reason that it is primarily more concerned about the communication between the devices or underlying media, right. And as we understand that there can be different sort of consideration, that there can be wireless, wired and type of things, and I need a media to transfer the data from one system to another, right. Now, incidentally, the mostly the mediums are mostly are carry signals through electromagnetic waves, so to say, and those are analog. So, is our digital thing needs to be converted to analog to convert to transmit, right. We have also seen that the predominant connectivity, because this requires a physical infrastructure to be in place, right. If I want to communicate across the world or across India also, then I require a physical infrastructure which will work at the backbone, right. And typically the physical infrastructure which is somewhat readily available with us is our telephone network, right. Though the bandwidth may not be that high, but nevertheless these days with the fiber etc., you can get higher bandwidth, but that the our telephone network is the basic framework of the things. And there are several service providers which which give services. So, our one consideration that if I can hook to this telephone network, then I can travel using this network and then at the other end get the data out of it, right. So, again we are talking about the physical physical layer consideration, right. Now, in order to have this to push it to this telephone network and type of things, we have seen there is we require a device called modulator at the end, at our end, at the source end, and a demodulator at the other end if the communication is this way or in other way, or rather we require modem or modems at the devices ends, right. Also, we have seen that the network interface card which comes with every system to support the network connectivity is primarily have both physical and data link layer properties, right. So, they have a physical layer consideration, that means you can connect RJ45 like our standard Ethernet cables or wireless connectivity or fiber connectivity, or in some cases coax connectivity etc., right. So, these are the physical connectivity. So, in other sense there should be a data link layer should be converting in them into appropriate signals to push the data across through the media, right. And when it travels to the media, that the whatever the means consideration for the medium comes into play, it will be there, right. Like there could be attenuation due to noise and type of things, or transmitting to a larger area, a larger distance and so on and so forth. So, those things will be there. So, so those will be there, and those are consideration, it varies from medium to medium. The things which is true for fiber are not true for, not always to that particular true for cable or wireless and type of things, right. So, again I just to reiterate that when we are talking about physical layer, we are considering the other layers are as they are in their place, the same thing like the routing protocols works, the TCP, that transport layer protocols works as they are supposed to work, application works as they are supposed to work. So, when you open a your email or a some network application at the upper layer, the speed may vary, right, due to the different type of physical layer, wired connection, wireless connection, fiber connection and type of things, speed may vary, but nevertheless the application, for the application it is a communication path which is available, right. So, this physical layer connectivity is the what we say that the last mile connectivity, or not only that bottom most layer of the connectivity, etc. And it dictates heavily that what should be the bandwidth, what should be the throughput, to some extent reliability, and so on and so forth. So, this lectures what we are trying to do, we are trying to look at different physical layer properties which may affect our networking capacity, right, and also little bit of try to not that go into deep into the communication, but little bit of consideration of the communications which may help us understanding our systems, right. So, that is the consideration. So, today also we will look at some of the features, and maybe in next lecture we will see few more features where the physical layer phenomena come into play. So, as we are discussing now, so two things coming now and then is the data and signal, right. So, analog and data and signal. So, what is data, what is signal, and how things are going on. So, whatever we are generating in our systems or working with is the data which has primarily two manifestation, 1 or 0, right. So, that is a binary representation of the things, and I generate the data for my purpose, and I do not care that how it things to be there. Whereas, at the backbone, as we are telling at the backbone, it is primarily electromagnetic waves need to be converted to some signal. So, data can be analog or signal or digital. Analog data are continuous, take continuous values. Digital data, whereas are discrete state and take discrete values, right. So, to transmit data must be transformed to electromagnetic signals, as the media can carry that electromagnetic signal primarily. So, data can be as I told, data can be analog or digital, signals also can be analog or digital, right, and analog signals can have infinite number of values in the range. A digital signal can have only a limited number of values within a particular range. In a data communication, we commonly use periodic analog signals and non-periodic digital signals, right. So, it is a periodic analog signals and non-periodic digital signals, that is the things which we consider mostly. We will see that what are the things. So, this is a typical example of a analog signals, and this is a typical scenario of a digital signal. So, you have digital things. So, I can consider that the positive has some positive voltage, negative voltage, I can have different level at the positive or negative type of things. So, signals, if we see what they have an amplitude, primarily periodic signal, they have an amplitude, they have some frequency, and they have a phase, right. So, frequency means how frequent, what is the after what time period it returns repeats the signal, whereas the amplitude is the highest value it attains on the positive side, or the on the negative side the minimum value it attains, and the things that dictates the amplitude of the things, and phase we will see that how much it is drifted from the origin, so to say. Later on we will see that how things will be there. So, at what time it is starting. So, signals with same phase and frequency, but different amplitude. So, this is starting at the same time, that is 0 and 0, having same frequency repeatability, this and this, whereas they have different amplitude, right. So, frequency and periodicity or periods are inversely proportional. So, frequency equal to 1 by t. So, it repeats every t time duration. So, frequency will be 1 by t or t equal to 1 by f. Signals with same amplitude and phase, but different frequency may happen. So, like this signal has repeatability is higher than this, like here 6 periods in 1 second, here 12 periods in 1 second. So, here frequency is typically 12 hertz, here 6 hertz, right. So, hertz is the unit of frequency, you will know. So, sine, in this case sine of the waves with same amplitude frequency, but with different phase. So, it is different start time, right. So, it is a sine wave is at different, so this is say amplitude and frequency on these three waves are same, but they have different start time. So, these are the three things. Now, one interesting thing you see from here. So, if I some way add this 3 sine wave to make a composite wave, right. I have 3 waves, I have a adder or which adds. So, what does add means that any point of time you see that what is the signal strength here 0, here it is say plus 5 or plus 10, here it is also 0. So, the I in my output here I put this as a 10, if this value if we consider as 10. Again at this particular junction or some junction I can basically put these vertical lines and calculate that how much value etcetera there, and then sum up the things and say this is my output signal, because it is a composite added signal, right. Had it been all in the phase, same amplitude etcetera, the things could have gone little higher at the thing, because the same repeatability. Now, this way I can have a composite signal type of things, like time domain as composite signal, like it may end up in making a composite periodic signal, right. So, we will see that. Now, we see there are 2 type of representation, the time domain and frequency domain plots of the sine wave. Like in this case it is a time domain plots, with time it is changing, the peak value is 5 volt 5, whereas we can have a frequency domain thing. How many frequencies are there in here? Only one frequency, 6 hertz. So, it is repeatability is 6 hertz. So, here also it is one frequency, and I know that what is the amplitude of the thing, right. So, here the amplitude of the thing. Now, if I have 2 sine wave, one with here we are having 3 waves, one with frequency 0, that is flat, one with frequency 8 and one with frequency 16. So, blue, then this pink and green, and then I can represent them into 3 things, right. Like if it is a 0 frequency, there is no repeatability. So, it is a DC thing, it is not repeatable, it is a constant thing, and that is at 15, whereas frequency with 8 is that pink is at 10, and frequency with 16, that is the green, is at this, right. Now, in this case again if I want to make them composite, so any point of time I go on adding what are the different values and do the composite signal, right. Like typically I may have some sort of a composite signal like this, and which is again repeatable. It may not be repeatable also, means it may be non-periodic, but in this case periodic signals we are having, because there is a inherent periodicity in the whole thing, right. So, there are in this typically, if that is sum up, and if you do in a graph paper also you can calculate. So, typically how many frequencies are there? There are 3 frequencies. If it is a sum we made it, so 0, 8 and 16 hertz, right. So, there are techniques like using Fourier transforms like that, and we can basically, if a composite signal is there, we can deduce it to this signal, right. Okay. So, that is a way of representation of the things. Okay. So, now we see the non-periodic composite signal. It can be the signal created by a microphone or a telephone set where when a word or 2 are pronounced, like. So, it is I am doing an analog talking in a microphone or telephone set. So, those things can be composite, can be so when 2 words are pronounced, in this case the composite signal cannot be periodic, otherwise it is repeatability of the whole things will come up. Usually the conversation is in information exchange, so repeatability is much less, and things are they are not periodic, they are non-periodic. So, bandwidth of a composite frequency, difference between the highest and the lowest frequency obtained from the things. Now, if I look at that composite frequency, it may vary from 0, that is no signal, to 4 kilohertz, that is our range of vocal and type of things. Also that what we see that range of our telephone plain old POTS telephone line is also typically in this range. So, that is the thing, and I can have any frequency within this range, right. So, this is more of a this sort of a structure. I can have different frequencies at this range, and it is a composite frequency. So, bandwidth of a composite signal is the difference between the highest and the lowest frequency of the thing, right. So, it is bandwidth is given by the highest and the lowest frequency. For that matter, any signal, the highest bandwidth and lowest frequency is the bandwidth of the things, right. Why we are breaking our heads on this? Because your communication channel may not allow all frequency bands, right. So, it has a own property, right. It has own material property, and then based on that all frequencies may not be allowed. So, it may allow a set of frequency. If it is some of the channels may allow a wider range, it may be allowing this range of frequencies in the things. So, your data signal or the data which you are generating at the endpoints should be able to put through this channel only, right. Or I need to know that how much the channel can allow and capacity a type of things, right. So, that is why we need to study that how is this type of bandwidth consideration, those are coming up in terms of this signaling or communication. Now, if we come to the digital signal, in addition to being represented by an analog signal, information can also be represented by digital signal. For example, 1 can be encoded as a positive voltage, 0 can be encoded as a as a 0 voltage. So, I can have 0 and 1. Digital signal can have more than 2 levels, even it can have 2 levels. One is here, it is only 2 levels, right, with 1 and 0. It can have more than 2 levels, right, different levels. So, I can have 1 1, 1 0, 0 1, 1 0, 0 0 and type of things, right. So, if this is more than 2 levels, then the more data is packed within the thing, right. So, effectively I can make more data communicate within that packed thing. So, it gives us a better throughput, right, but not always feasible, we will see. So, a digital signal has 8 level. How many bits are needed per level? We can calculate the bits as use a formula that log 2 8 equal to 3 bits. So, if it is 8 level, so I can have 3 bits to the power 3 is 8, right. Each signal level is represented by 3 bits. So, bit rate is the number of bits sent in 1 second expressed in bits per second, right. So, assume we need to download the text documents at the rate 100 pages per minute. So, if that is my consideration, what is the required bit rate of the channel? So, if the page is an average of 24 lines with 80 characters each line, we assume that one character requires 8 bit representation. The bit rate is 100 into 8 into 80 into 8 equal to 1 point so that is 1.63 Mbps. So, that is the bit rate for this type of things, right. So, there is a very flat way of calculation, there will be lot of other consideration, but nevertheless we can have a come to a thing. Similarly, a digitized voice, as we see in somewhere that it is digitized as a 4 kilohertz and we need to sample the twice the highest frequency, then we can have a bit rate. Similarly, what is the bit rate of HDTP? We can calculate with the rate of what is the refresh time and so forth. So, this way I can calculate the bit rate. There is a concept of bit length. The bit length is the distance of 1 bit occupies in the transmission medium, right. So, bit length is the distance 1 bit occupies in a transmission medium. So, bit length equal to propagation delay into bit duration. So, how much duration is there along with the propagation speed is give me the bit length. So, time and frequency domain, periodic and non-periodic digital signals. So, this is the representation of this if I have a periodic signal, and if you have a non-periodic digital signal, then the frequencies are both cases it goes to infinity, right. So, end of the things, but in order to reconstruction I may not require those frequencies which contribute very less into the things, right. So, there are different considerations from the communication point of view. There are considerations like take that which harmonics of the things will be there, odd harmonics and type of things, how many you can go to have a faithful reconstruction. So, both bandwidths are infinite, but the periodic signal at discrete frequencies whereas the non-periodic signal has a continuous frequency, right. So, there is another consideration comes up when we try to transmit data over a channel, right. What we say it is a transmission impairment, right. Signals travel through transmission media which are not perfect. The imperfection cause signal impairment, right. This means that the signal at the beginning of the media is not at the same or the thing. So, you send something and it is something got in not the same thing. The typically three categories of things are there. One is the attenuation, one is distortion, another is the noise. So, this type of three type of situations which causes this type of impairment. In case of attenuation, loss of energy, when the signal and the simple or composite travel through the media, it loses some of its energy in overcoming the resistance of the media. To compensate to this loss, the amplifier are used to, or signal regenerator I should say, instead of amplifier are used to regenerate the signal, right. So, it has degraded and regenerated. Suppose a signal travel through a transmission media and its power is reduced to half. So, it was P and now it is P by 2, or sorry P1 and now P2 is half of P1. In this case, the attenuation loss of power can be calculated as like this, right. So, a loss of 3 dB or minus 3 dB is equivalent of losing half of the power. That is why that 3 dB loss etc. we come into play, that is a 50% power is lost. Another means another source of impairment is that distortion. Signal changes its form or shape, right. Distortion can occur in composite signal made of different frequencies. So, each what happened, each signal component had its own propagation speed through a medium and therefore, its own delay arriving at the destination. So, differences in the delay is create a difference in the phase, which in turns not exactly the same as the periodicity of the periodic duration. So, let us see, I send a composite signal which has number of frequency component. Incidentally, because of this channel characteristics, that is the channel properties, the different frequencies get different type of say delay of reaching a thing. So, there are no attenuation per se, but there are different delay, and while it reaches the things, then what happened, it is now it is at different time duration or period duration. So, when you reconstruct, you can't reconstruct the same composite signal, or in other sense you don't get back the same data. So, if it is here you see it was in phase data, like this is same time, this in phase data. When we made a composite signal, due to impairment it received there, you decompose the signal, it goes for a impairment, like there is a shift here, here with respect to this. So, there is a phase shifting will go for a problem of the overall data. And finally, we have this noise as the impairment, right. Several type of noise such as thermal noise, induced noise, crosstalk, impulse noise may corrupt the signal, right. So, there can be different noise. So, thermal noise is a random motion of electrons in wire which creates an extra signal not originally sent by the transmitter. So, that is the thermal noise. Induced noise comes from source such as motor and appliances, from different sources induced noise. So, that is induced in the thing. Crosstalk is the effect of one wire on the other. One wire acts as a sending antenna, other as a receiving antenna. So, it is a crosstalk when two things are moving, two things are in nearby location, and there can be impulse noise is a spike signal with very high frequency with very short time that comes from the power lines, lightning, etc. So, there is a impulse and the impulse noise. So, these are the different category of noise which distorts or creates problem in the signal, right. So, in other sense there are impairment and there will be a challenge in reconstructing the things. So, this what we see, this noise also plays a important role in faithful delivery of the signal at the other end. Now, these are the things which are there, right. We need to, irrespective of this, we need to send data and type of things. So, there is one side, there are lot of development or things are going on, that how more improved channels can be created, like you get a more faithful transmission when you do you work with something called in fiber type of channels, and type of, and then other things that whether I can better way encode or modulate the data, so that so it can be sent to even to some extent not so good channels and type of things. Another metric come into play, or we listen now and then, is the signal to noise ratio. To find the theoretical bit rate, we need to know the ratio of the signal power to the noise power. So, average signal power by average noise power, that is important. So, get the SNR type of thing. So, average signal and average noise power are considered, as these may change with time, right. A high SNR means the signal is less corrupted by the noise, or a low SNR means the signal is more corrupted by noise. So, this is the consideration, means that plays an important role, right. Since SNR is the ratio of two powers, it is often described in decibel, and SNR dB defined as SNR equal to 10. So, there is a typo here, 10 log 10 SNR. So, it should have been in the same line. So, similarly, I can calculate a SNR and SNR dB using this, right. Data rate limits. So, data rate depends on primarily on three factors. One is the bandwidth available, how much bandwidth you are available, level of signals, what are the levels of signals, it is a 2 level, 4 level, what are the levels of signals, and quality of the channel level of noise, right. So, what is the quality of the channel, right, like the fiber, some fiber cable, there will be a different quality aspect than if you have a wired cable and type of things. So, quality of the channel or the level of noise plays an important role. Increasing the level of the signal may reduce the availability reliability of the system. So, if I go on increasing the level of the signal, because as we say that if I go on increase the thing, it is more compact and I can get better, but it hurts the reliability of the things. More granular things, more finer things, there will be more likely chance of disruption or distortion and type of things. So, there are two theoretical formulas which help us in estimating that what should be my bit rate and type of things. So, one is Nyquist for noiseless channel, another is Shannon's proposed by Shannon for noisy channel. So, we just see quickly that what they say, that Nyquist bit rate formula defines the theoretical maximum bit rate is the 2 into bandwidth into log 2 base 2 with L is the number of levels, right. So, that is the theoretical thing in a noiseless channel. So, consider the noiseless channel with bandwidth 300 hertz transmitting a signal with 2 signal level. The maximum bit level can be calculated as 2 into 3000 into log 2 base 2 equal to 6000, right. Consider the same channel transmitting a signal with 4 signal levels. So, instead of 1, it has a 4 signal levels. So, what it goes on? It basically say 2 into this, it should be 12,000 BPS. So, changing the signal level, I can go up in the bandwidth, right. So, for noisy channel, there we have that Shannon's capacity. In reality, we cannot have noiseless channel, right. So, there will be some form of noise or not. The channel is always noisy. In long back in 1944, the Shannon introduced a formula called Shannon capacity to determine the theoretical highest data rate for the noisy channel. So, what is the highest data rate it can support? So, bandwidth into log base 2 1 plus SNR, that is the highest level. Like consider an extremely noisy channel in which the value of the noise to signal to noise ratio is almost 0, right. So, there is all you made number of levels etc., but the noise is so high, the SNR value is nearing 0, right. So, very low signal, say channel capacity C equal to B log 2 1 by SNR, and then what we can find out that irrespective of whatever you do, finally it ends up in the 0 or near 0. There is no transmission is possible, so much noise is there. This means the capacity of the channel is 0 regardless of the bandwidth. In other words, we cannot retrieve any data through this channel. right. So, this is the way it gives say some limitation of the means boundary of the things, that what is the highest level you can reach with this type of channel and type of things. So, if you see for practical purpose, when SNR is very high, that is we assume that the SNR plus 1 is also almost the same, like if we have a huge SNR. So, practically 1 plus SNR is same, or in other sense the theoretical channel capacity can be expressed as C equal to B into SNR dB by 3, right. So, based on the things, we have a channel with 1 megahertz bandwidth. The SNR of this channel is 63. What are the appropriate bit rate and signal levels, right. So, this is the thing we want to find out. Like first we use Shannon's formula to find out the upper limit, right. So, it is B log 2 1 plus SNR and something 6 Mbps. So, that is the upper limit. Now, the upper limit, the better performance, we choose something lower, that is 4 Mbps for example, and use the Nyquist formula to find out the level. So, putting the Nyquist formula, we found out the level equal to 4. So, somehow means if we try to look at the summarize the thing. So, what we use, the Shannon capacity gives us the upper limit, the Nyquist formula gives us the signal channel. Now, see our this basic consideration helps us in finding the what could be my channel capacity, what amount of rate we can get. This may allow me to plan something, that what should be the data transmission time, etc., and type of things, right, which is very much needed for different consideration. So, let us with this thing, that basic fundamental way calculation, that this digital signal, digital data and signal, and analog data and signals consideration, how we can have some sort of estimate of approximate bit rate and the signal levels, that we have seen, and this will help us in estimating separate thing. So, with this let us conclude today. We will be continuing our discussion in our next lecture on this physical layer. Thank you.